From geometry class, there's a description of conic sections which involves what they call a point, which is called a focus, and a line, which is called a directrix. And you look at all of the points. Sorry, I'm not sure why that just jumped on me here. I'm going to look at all of the points in the plane where, so pick a point here. I'm going to look at the distance from that chosen point to the starting one here, and I'm going to look at the distance from that point to the line. So if this point is xy, and let's just for the sake of argument say that, why does this keep moving on me? That's why. Let's just for the sake of argument say that that point is the origin, which would put this line, let's just call it a vertical line, at x equals d. Right? We look at the ratio of these two distances here. Let's call this one r and call this one, well, this one's pretty easy to calculate, right? Because it's just the difference in the x-coordinate here minus there. So this would be d minus x. So if I look at the ratio of r divided by d minus x, and if I say I want all the points xy where this ratio is some constant, let's call it e, then I get a bunch of points. In a geometry class, you would learn that you get what's the conic section. If e equals 1, then you get a parabola. With e equals 1, notice that we're saying that these two lengths are the same, that this ratio is equal to 1. So you end up with the point with e equal 1, let's put it here. You got this point, you got this line. The point right in the middle certainly would have this point and that point. And then you've got this whole other thing. That this distance here would be the same as that distance here. This distance would be the same as that distance. All right. This point right in here is called the focus. The line that we started with out here, this line, is called the directrix. And in the case with e equals 1, what we got was a parabola. If e is, let's say, less than 1, if e is less than 1, then let's draw this back in again here. Here's my focus here. Here's my parabola. I'm using points that are closer to, so if e is less than 1, it means the numerator is smaller than the denominator. So this distance is going to be less than that distance. I am going to get an ellipse, I believe. Yeah, then it turns out that, of course, e is positive as well because we're talking lengths here. It turns out that the set of points that you get looks more like an ellipse. And if e is bigger than 1, so we're talking that the distance from here to here is bigger than that one, then what we end up with is an hyperbola. Not obvious, but we also can get points behind us here. That when you look at this distance divided by that distance, so this is the bigger one or smaller one, or you could look at, let's say, this distance divided by that distance, you might end up with a similar amount, although that has it looking like I've got it drawn too close. So let me try drawing this a little bit further away so that this distance divided by that distance might be the same as this distance divided by that distance. Right? There's a matter of, are you measuring d minus x or x minus d? When we're talking distance, it's not going to make any difference, so that there's an absolute value that gets thrown in that gets the stuff over here as well. But this is an hyperbola. All of them come from the relationship of looking at a distance away from the origin and a distance away from some fixed line, and saying that the ratio is going to be some constant. Depending on the value of the constant, you get hyperbolas, that constant's bigger than 1. You get ellipses if that constant is less than 1, and you get parabolas if it's equal to 1. Okay. Now, I should do a little algebra here to show you that you do get the equation of a conic section. So let's do that right now. So when I look at this, r is the distance from the origin, which if you got some point xy, the distance to the origin is, look at Pythagoras, the square root of x squared plus y squared. Okay. So changing the r into that, we get this. Let's multiply both sides here. So I got x squared plus y squared under the square root equals e times d minus x. Then square both sides. I've got x squared plus y squared equals e squared times d minus x squared. And see, at this point, I feel a little bit better about it in that I was assuming that d was bigger than x. I was assuming that all the points that I'm choosing are to the left of where the line was. But I can get stuff over here too if I allow the distance to be x minus d. Well, d minus x, x minus d, either way, when you square them, you're going to end up with the same value. So this d minus x squared would also be the same as x minus d squared. And so now I'm sort of taking account to maybe being on the other side of that line. Anyway, this you can see now when I multiply it out, x squared plus y squared equals e squared d squared minus 2e squared xd. Actually, let's put it as dx plus e squared x squared. This is all x's and y's to either the first or second power. That's what conic sections are. As you'll learn in a pre-calc 1 class. So I can collect some like terms here. I've got x squared times 1 minus e squared when I get the two of them together. I've got a plus 2e squared dx, and I've got a plus y squared equals e squared d squared. Now, before doing any other algebra here, what I remember about conic sections is that if it was just an x squared plus y squared equals a constant, that's a circle. When the coefficient in front of the x squared was different than the coefficient in front of the y squared, well, that's going to make it an ellipse or a hyperbola, but I can tell by the signs that these are both pluses. There's a plus x squared and a plus y squared. So this is going to be an ellipse. The special ellipses are when the two coefficients are the same, right? This is not a special ellipse. It's got something else. Some different coefficient in front of the x squared than in front of the y squared. Also, when I have this linear term here, this is just x to the first power, it means that there's been a shift in the x direction. I can figure out what that shift is by completing the square on x's and see what happens. And then to see exactly where it is and what the major and minor axes are, I'm going to divide by whatever ends up over on this side so that there's a 1, and I can look at the denominators, right? And that gives me the major and minor axes. And I'm going to do all that work. But the point that I can see here is that this is going to be a conic section. Now notice, there's a couple of things that happen based on E, right? Right there. If E is, let's start with less than 1, then E squared is also less than 1. Actually, the absolute value of E is less than 1. Well, I don't care about absolute value. If E is less than 1, then 1 minus e squared is positive, and you got a positive in front of the x squared, a positive in front of the y squared. We're talking an ellipse, right? Is that what we set up above? If e squared was less than 1, yes, we were looking at an ellipse. when e squared is equal to 1, not e squared, well, yeah, if e equals 1, then 1 minus e squared is equal to 0. And what we have here is a 0 in front of the x squared. This is not quadratic in x anymore. This is only linear in x and quadratic in y. What we're getting here is a sideways parabola. Right? That x squared term goes away. On the other hand, if e is bigger than 1, then 1 minus e squared is actually negative because the e squared is bigger than 1. And the sign, the SIGN here, of the x squared, the coefficient in front of the x squared is going to be negative, where the coefficient in front of the y squared is positive, and we're looking at an hyperbola. Hyperbola. There we go. Okay. So there's that e plus bigger than 1, less than 1, whatever, determining whether an ellipse, parabola, or hyperbola. So there is this notion of the ratio of the two distances, the ratio of the distance from a point to some fixed point or from some point to a given line, and you look at the ratio of those two distances. If that ratio is a constant for every x on this, for every point on this curve, then you've got a conic section. What type of conic section depends on what that value is right there. Okay. This is called the eccentricity.